All right, Lobos. Welcome to my own flipped video. This is my first attempt at really doing this, so if it's wonky, go with it. All right. The last force that we really need to learn in depth before our test, which is November 11th, a week from this coming Tuesday, is the spring force. So in class, we've talked about the friction force now, and we kind of have a handle on the different types of friction, kinetic friction, static friction, and how they, when they're applying and how they interact with objects. And the last force that we talked about on the first day when I introduced all of these is spring force, that we really need to get a better idea on the details. So a spring force, and this is a slight variation of the definition I gave you, but it still works. Basically, it's a return force exerted by an object attempting to regain its original shape, or to return to its original shape. And it's a little weird thinking about an object trying to do something by itself, but you get the idea. And that's when I stretch this spring, it's exerting a force on my fingers trying to pull it back in, because it wants to go back to this shape right here. So as I pull it out, it's trying to go back the other way. Now, you have like I said in class, if you have a little spring, like, I don't have one with me, but that, like in your mechanical pencils, for instance, that you can squish. Well, when you squish the spring, it's trying to push back out, and it's trying to return to its original position. But it doesn't just have to be a spring made of metal. It can be like my meter stick here. If you grab a meter stick and pull it back, it wants to go back to its original shape. It wants to go back to its original shape. Even if you stand on a table and the table kind of is bending a little bit, it's actually holding you up with a spring force, because really what's going on is that the molecules are you're bending the whole shape of the table, and it's held together by the molecular bonds, and they want to go back to where they were before, so they're pushing back up on you, which is, well, that's what's really holding you up when you're looking at a table, is kind of the spring force built into the molecules of the table. Okay, but let's get a little more scientific about this. We need to figure out, for instance, how is force related to the distance the spring stretches, and what direction the force is, and that kind of thing. So when we actually do problems where we have things hanging from springs, we know what's going on, and we can analyze this fully. So here I have a kind of a nice little delicate spring. I'm going to hang up from my little apparatus of science, and I have two 20-gram masses. Two 20-gram masses. And then I'm going to hang them from here. We're going to measure it and see what happens. Well, if each mass is 20 grams, so it's 20 grams, times 1 kilogram divided by 1,000 grams. This is, then we can divide, those cancel out, the grams cancel out, we divide the 20 by 1,000, so you go 1, 2, 3, we get each of these is 0.02 kilograms. So the masses of things, they're not very big. Now, when I hang them from the spring, what's going on? Well, on the mass itself, there's two forces acting. I'll go to put it up here so we can see. There's two forces acting on the mass. There's the force of gravity pulling down, and there's the spring force pulling back up. And the symbol that we use for that is F sub S. Spring force. The spring force is pulling back up, and when it stops jiggling up and down, it's stationary. Since it's stationary, these two forces must be equal, because there's no acceleration on the object. All right. What is this force here that's actually pulling down on the spring? Well, it's the force of gravity acting on the object, which we know is just force of gravity acting on the object is just the mass of the object times the acceleration due to gravity, which is 9.8 meters per second squared. Let's figure out what this is. 0.02 kilograms times 9.8 meters per second squared force of gravity is equal to, I need a calculator. All right, 0.02 times 9.8 equals 0.196. So we'll round up to 0.2. That's okay. So the force, so in other words, we're using, yeah, we're just, here, for lack of a better, to make it prettier, we'll use 10 meters per second squared for gravity. Just for the sake of prettiness for right now. So let's go 0.2 newtons is the force of gravity pulling on this object. So the weight of the object is 0.2 newtons. All right. So let's find out what effect does that 0.2 newtons have on the spring. All right, Lobos, I'm cutting this part of the video in because my experiment that did it in the last one didn't work very well because my spring wasn't a very ideal spring. So I'm going to try with another spring that I dug out of the lab and see if that works a little better. So now the force that I'm going to be applying each time pretend you didn't see that. You're about to learn that. This is like Back to the Future. Okay, the force, let's see. This is a 50 gram mass. The 50 gram mass, let's see, 50 grams. Let's find out how many kilograms it is so we can find out how many newtons of force the mass will be pulling down with on the spring. So 50 grams times 1 kilogram divided by 1,000 grams. Grams cancel out, 50 divided by 1,000. We'll each move the decimal place over 3. So you get 0.05 kilograms. So 0.05 kilograms is our mass. We're going to multiply that by the force of gravity. Let's see, is mass times deceleration due to gravity. So the force of gravity acting on these 50 gram masses is 0.05 kilograms times, I'm just going to use 10 to keep the number prettyish for the acceleration due to gravity. Technically it's 9.8. And you get, notice that I didn't plug in negative 10 because the force, this is already pointing down. So we plugged in negative 9.8 a lot when we did kinematics, but don't just automatically plug in negative 9.8. Always think about what direction these things are happening in. Sorry, aside. All right, 0.5 times 10 is 0.5 newtons. Nice, easy, happy number. Force of gravity acting on this object, 0.5 newtons. This is the object's weight. So I'm going to apply half of a newton to this spring, and we're going to see how far it stretches. That's what we're trying to figure out. We're trying to figure out what's the relationship between the amount of force applied to a spring and how far that spring stretches. So the initial position of the edge of the spring is right at 55.5 centimeters above the table. So the initial position is 55.5 centimeters divided by 100 to turn into meters equals 0.555 meters. That's the initial position of the edge of the spring. So I'm going to apply half a newton of force to it and see what happens. It stretches. I'm going to now measure its next position. The final position of the spring, it's kind of jiggling, so it's a little difficult to tell, is 47.9. Final position, so 0.479 meters, which gives us a displacement, because this is a displacement of the spring. The displacement, 0.555. Final minus initial, 0.479 minus 0.555 equals negative 0.076. Was negative 0.076 meters. And that's just right, because negative was down and the displacement was in the negative direction. All right, So when I added half a Newton of force, the string stretched in the negative direction 0.076 meters. Let's see what happens if I add another half a Newton. Now its final position is 38.9 or so. So let's see, over here, next trial, our initial position, I'd say 38.9 or so centimeters. Sorry, 0.0389 meters. Our initial position was where we left off over here, which was 0.479 meters. So what's our displacement in this case? Well, 0.389, whoa, sorry, 0.389, not 0.0389. Yeah, 0.389 minus 0.479 equals 0.09. Okay, that's closer. Right. 0.09 meters. Yep, okay, 0.09. All right, sorry, negative 0.09. Now, this is like a perfect thing. When you do a lab that has to do with this, you're going to need to kind of take lots of measurements, find some averages, or plot them on a graph, and use the line of best fit. So if we did this a little more scientifically, we can plot the force exerted on the spring by the distance the spring stretches. And we would get at 0 is there's 0, because when I don't apply a force to the spring, it is not stretching at all. It is at its kind of equilibrium 0 position. This is totally not scientific, so don't do this in your lab journals. Use graph paper, but roughly you'll get something like this. It should appear to be relatively linear. Now, if it was perfectly linear, these numbers would have been the same, but I was off by 0.014, which isn't too bad, but it's still off by a little bit. And the slope of this line tells us something. It tells us how much force is required to stretch the spring a certain amount. Or, and another way to read it is that if you stretch the spring a certain amount, how much force is the spring going to pull back with? Those two things are two versions of two halves of Newton's third law. If you stretch a spring, you apply a certain force on the spring, what's the distance it's going to do? But also, if you stretch a spring a certain distance, how much force is going to be pulling back? Because the force that takes the stretch is the same force with which it's going to be pulling back, because that's the force pair. I stretch spring, or that's not that. I pull string, string pull me. I pull string, string pull me. Okay, this relationship now between the force and the distance, this is what we call Hooke's law. And I'll now cut back to the other video, which might repeat some of this, but you'll be okay. And ideally what would have happened is this. And you're going to do a lab on this, so hopefully when you do your lab, I'll make sure and find better springs. And that the force required, hold on. So the force required to stretch the spring, if we plot that versus the displacement of the spring itself, we would have gotten 2 points, and that, including actually 0, because if you don't apply force at all, the displacement of the string is 0. So you get these points that should form a very linear line. Because Hooke's law says that for every amount of stretch that you pull a spring, you add an equal amount of force. So if I stretch it 10 centimeters, I'll get a certain amount of force, or it's going to pull back with a certain amount of force. Or in other words, it takes a certain amount of force to stretch it 10 centimeters. If I stretch it 20 centimeters, then it takes exactly twice that force. If I stretch it 30 centimeters, then it's going to take 3 times that original force to stretch it 3 times as far. They're directly proportional to each other. And the equation itself for Hooke's law looks like this. The force of the spring is equal to negative K and times the displacement. Negative K, or K itself, K is called the spring constant. And it's not a constant in the sense of like 9.8 meters per second squared. It's not a constant for any situation, but it's a constant for that spring. A certain spring will have a certain spring constant associated with it. Because this spring constant describes basically like how strong the spring is. So let's look at what are the units of this, and what is this constant really kind of telling us? Well, let's solve for K. We'll talk about the negative sign in 1 second, but let's solve for K. We find that K is equal to the force required to stretch the spring divided by the displacement of the spring. And this displacement here is a vector c. So in other words, it tells you, and okay, so sorry, this is force is measured in newtons, and displacement is measured in meters. So the units of K are newtons per meter. Newtons per meter. Now that actually makes sense because it means like how many newtons do I have to stretch for every meter that I want to stretch the spring? How many newtons do I need to apply in order to stretch the spring a certain distance? So the spring constants are measured in newtons per meter. How many newtons does it take to stretch it a certain amount of distance? That's what K is a measure of. And every spring is going to have its own kind of unique K. And we'll do a lab, hopefully, probably, where we discover the spring constant of whatever spring your team has. Now there's a negative sign. Why is there a negative sign right here? Well, you'll notice that when the displacement was negative on our little experiment, in other words, when we added the force, it was pulling down. The force is pulling down on the spring. So, but when you pull down on the spring, what direction does the spring pull back? Well, I just kind of said it, but it pulls back. It pulls back the opposite direction. So if my displacement is negative, the force that spring is exerting on the weights themselves should be positive. In other words, pointing in the opposite direction. So my displacement is negative, which is down in this case. So my force exerted by the spring on the little weights is positive. So in other words, going up. That's what the negative is there to do. So if my displacement is negative, so I have a negative, negative change in x, times a negative k, negative times a negative will equal a positive, which means our force will be pointing in the opposite direction. And this is what I was saying at the very beginning of the video, is that if you stretch a spring, it wants to pull back in. But if I compress a spring, in other words, my displacement is in the opposite direction, it wants to push back out. So the force is going to be the opposite of what it was when I stretched it. So the spring always is trying to do the opposite of what you've done to it. If you stretch it, in other words, you apply whatever positive force, it's going to pull back the negative force. But if you push it in other words, you applied a negative force, it's going to push back with a positive force. So to kind of conclude, sorry my experiment was a little crazy. In general it worked, it was close. It was within probably 30% error, which is a very good error. But you can tell that at the first mass stretched it. So here's the thing, we'll use a rougher estimate so it looks a little better. Won't be so accurate. About that far. I do it again, and you can see it's close to being about the same. It's a little further, and that's because this is probably not a perfect spring. But in general, this is the law that we're going to be dealing with, and this is called Hooke's law. So we dealt with understanding what a spring force is, why it's doing what it's doing, and then we looked at the fact that when you stretch a spring, the force acts in the opposite direction, or when you compress the spring, it forces back the opposite way. I tried to show you an experimental version of Hooke's law, that whenever you stretch the spring a certain amount, for every amount that you stretch the spring, the force changes proportionally. So if I double the displacement, I double the force. Or vice versa, if I double the force pulling on the spring, I'm going to stretch the spring twice as far. K, we discovered, is a measure of kind of how stiff and tough the spring is. The bigger the K, the more force I have to apply to stretch it a certain distance. The bigger the K, the more force I have to apply to stretch it a certain distance. And K is the slope of this graph, by the way, I should have said that. Because this is a linear line. Y equals m times x. M, our slope, is just what K is. So if you can plot on a graph the force required to stretch the spring versus how far the spring is stretched, the slope of that line will tell you the spring constant K. Okay, any questions? Write them down, ask me at the beginning of class tomorrow. Thank you for putting up with my silly little video.